This is our second lesson on trigonometric identities. In the first lesson, which you could go take a look at if you haven't gone through it already, in the first lesson we made use of the relatively new definitions for sine theta, cos theta, and tan theta, which are expressed in terms of the point xy and then the distance from the origin to the terminal arm, which is represented by r. So that equation ends up being a Pythagorean relationship. So hopefully that's familiar to you. And from there, using these definitions of sine, cosine, and tangent, I was able to show that there is an identity called the quotient identity where tan theta is actually equivalent to sine theta over cos theta for any values of theta or any valid values of theta. And then there's something known as the Pythagorean identity. It's called that because it looks a lot like the Pythagorean theorem. And in this case, we end up with sine squared theta plus cos squared theta equals 1. Both of these are very common. These are the starting point for trigonometric identities. We've also, this is more of a review, but we've been making heavy use of it in this course as well, which is just the idea of the sine and cosine and tangent can be defined also in terms of different sides of a triangle. So we need to keep in mind both of those sets of definitions for sine, cosine, and tangent. So what we're going to do with this lesson is we're actually going to look at some different definitions. And you'll notice here, at first you might think that this is exactly the same slide that I showed you on the previous page. But the previous page has sine is opposite over hypotenuse. Whereas on this page, I now have hypotenuse over opposite. So what I've done is I have flipped. So when I had sine of theta is opposite over hypotenuse, now if I reverse or take the reciprocal, I end up with hypotenuse over opposite. That's given this new name called cosecant. If we do hypotenuse over adjacent, hopefully you recognize that that looks very similar to cosine, except for it's the reciprocal. That's called the secant. And then adjacent over opposite is the reciprocal of opposite over adjacent. So this is a different trigonometric ratio. It's called cotangent, and it is the reciprocal of tangent. And I've summarized this, the fact that we have these reciprocal identities. Cosecant has a short form CSC, just in the same way that sine is SINE, but its short form is SIN. Secant is SEC. Cosine, of course, is cos, so secant is 1 over cos. Cosecant is 1 over sine. Cotangent is 1 over tangent. And these are known as the reciprocal identities. And now finally, I wouldn't expect you to write this down in class, that's why it's got a blue background, but it's an interesting thing to follow through. So let's start off with the Pythagorean identity. But what happens if we divide everything here by cos squared theta? So we have to divide everything, both sides. So I'm going to go ahead and rewrite it. Sine squared theta plus cos squared theta equals 1. And then as is suggested here, this is an equation, so I can, whatever I do to the left side, I do to the right side. So there's nothing wrong with dividing everything by cos squared. But now I end up with some interesting results. Sine squared divided by cos squared, well, sine over cos is tan, so sine squared over cos squared is actually tan squared theta. Plus cos squared divided by cos squared, well, that's a thing divided by the same thing. That's just equal to 1. And then 1 over cos squared, well, we just talked about the fact that 1 over cosine theta is one of the reciprocal identities. It's actually called secant of theta. So 1 over cosine squared is the same as 1 over cos all squared, and that must be equal to secant squared. So we end up with this new identity, tan squared theta plus 1 is equal to secant squared theta. Now this identity is based off of the Pythagorean identity. So although I'm aware that this identity exists, I'll be honest with you, I don't bother memorizing this. If I happen to remember it, great, but otherwise, I always remember the Pythagorean identity, and I know I can divide by cos squared, or, as I'll show you on the next page, I can also divide by sine squared, and let's see what that gets us. It's going to get us a different identity. Now I'm going to divide that Pythagorean identity by sine squared theta. Sine squared divided by sine squared is equal to 1. Cos squared divided by sine squared. That's another one of the new identities we looked at, which is that cos theta over sine theta. Well, cos theta over sine theta, maybe I need to take one step back from there. We learned that tan theta is equal to sine theta over cos theta. So this ratio with sine and cosine is familiar. So if tan theta is equal to this, then 1 over tan theta must be the reciprocal, which means I could say cos theta over sine theta is equal to 1 over tan theta. But that's the same as cotangent theta, which is one of our new reciprocal identities. But here I have cos squared over sine squared, which means this must be cotangent squared theta, equals, and then 1 over sine squared theta. Well, what's 1 over sine? 1 over sine is cosecant theta. So 1 over sine squared is cosecant squared theta. So that gives us another new identity. That's just a variation of the Pythagorean identity. So putting all of these things in one place, we started with our previous lesson. We looked at the quotient identity, we looked at the Pythagorean identity, and I showed you where those come from. Now we have the reciprocal identities. I'm not showing you where those come from. These are just by definition. So I'm not trying to justify the reciprocal identities, just in the same way that I never justified what was sine theta, cosine theta, or tangent theta. They were given by definition. And then I can use these reciprocal identities along with the Pythagorean identity to come up with these other two useful identities. So we'll come back and refer to this as we work through this so you can see where I'm making changes and why. So let's go ahead and do an example. This is from the worksheet that's listed on the web page I'll be handing out in class. I'm trying to prove that the left side is equal to the right side. It's very important when you do identities that you actually break these things up. One of the strategies that I suggest is that you start with the more complicated side, and I think I could make the argument that the right side, both sides have one of these new reciprocal identities, but the right side also has a fraction or a quotient itself. So I'm actually going to start my work on the right side. So that's the cotangent of theta divided by the cosine of theta. I'm going to make a replacement. Now, I'm actually going to make this replacement. Normally, I would make this replacement in one step, but I'm going to take 2 steps over here in rough work so I don't lose anybody. Cotangent is defined as 1 over tangent. But tangent itself is defined as sine theta over cos theta. So this is 1 over sine theta over cos theta, which turns out to be cos theta over sine theta. So cotangent is just the reciprocal of tangent. So since tangent is sine over cos, cotangent must be cos over sine. So I get cos theta over sine theta. and that's still divided by my original denominator, which is cos theta. I remember that this is the same thing as this denominator is cos theta over 1. I just remember that that can be represented as a fraction because that's going to allow me to write this as cos theta over sine theta. But now I'm going to multiply by the reciprocal of that fraction, which is 1 over cos theta. And that has this very nice result, which is I divide out the cos thetas. They both turn into 1s. So I end up with, and I'm going to write an extra line here, I end up with 1 over sine theta, but that's just the reciprocal of sine theta, which we have learned in this lesson is actually the same thing as cosecant theta, but cosecant theta is the left side. That's what I'm looking for here. So I have actually changed the right side into the left side. And so therefore my identity is true. Okay, this one's quite a bit more difficult. Taking a look at this, I think it just looks ugly no matter how you think about it. This is another one from our worksheet. Prove that cosecant to the fourth of x minus cotangent to the fourth of x equals cosecant squared of x plus cotangent squared of x. This just looks awful in general, but the left side has exponents of 4, which is worse than the exponents of 2. So I'm going to grit my teeth and I'm going to at least take a look at the left side. Cosecant to the fourth of x minus cotangent to the fourth of x. Now to do this one, we're actually going to use a mathematical trick, and to a certain extent we're going to use a mathematical trick twice if you need to. The first thing I recognize is that this is to the power 4, this is the power 4. We've got something that's even here. I'm going to say let A represent cosecant of x, B represent cotangent of x. So that means my left side is equal to cosecant is A, so this is A to the 4 minus B to the 4. Okay, that's helped a bit, but it's still not the whole way there, but I can get us the rest of the way here. What I see here, A to the 4th minus B to the 4th, I would really like that if that was A squared minus B squared. So actually, you know what? I'm going to go ahead and do another substitution. I'm going to let's see, I'm going to let P be equal to A squared and Q is equal to B squared. So now my left side is equal to, well, if P is A squared, what's A to the 4th? That would be A squared squared, or P squared. What is B to the 4th? That would be Q squared. Now, do you need to go this far, and do you want to be writing stuff out this way? No, absolutely not. But I'm just trying to show you that there are things that you can do when you're stuck, patterns that you can see. When I see a power of something minus a power of something, the relationship between powers that I'm most comfortable with would be a difference of squares, which I've managed to work it down to here. Well, this is just P minus Q times P plus Q. But if I switch back to my A's and B's, well, what is P minus Q? That would be A squared minus B squared. And this one would be A squared plus B squared. And let's go all the way back. So now what this becomes, instead of A squared, well, that's cosecant. So this first bracket, A squared, is actually cosecant squared x minus cotangent squared x. And then the second bracket is cosecant squared x plus cotangent squared x. Just going to move all of this stuff a little further to the right, get it out of the way. Okay. Now, it's always a good idea when you're doing your trig identities to be thinking about where are you trying to get. In this case, our target is the right side. So take a look at what I've got on the left side here. I could have even started that right away. On the left side, I have powers of 4, but on the right side, I have powers of 2. So how can I change powers of 4 into powers of 2? A difference of squares. Now, if you take a look, cosecant squared, cotangent squared, cosecant squared plus cotangent squared, I actually have the right side right there. So what do I need this thing to be? If I can show that this thing is equal to 1, then I would have the right side. Okay, can I show that that thing is equal to 1? Now I'm trying to fit everything onto this single page, so I'm going to just break this for a moment and remind you of one of our other identities. So I'll go back to here. Here is an identity that involves cotangent and cosecant. Cotangent squared theta plus 1 equals cosecant. I'm just going to rewrite it for you here. Cotangent squared theta plus 1 is equal to cosecant squared theta. But I have here cosecant squared x minus cotangent. So what I need to do is take this cotangent to the other side. But of course, this positive cotangent squared becomes negative. So I get 1 equals cosecant squared theta minus cotangent squared theta. And that is a really nice result for us because that is exactly what I've got in this bracket. And it is 1. So this is equal to cosecant squared x plus cotangent squared x. The other thing was just equal to 1. Maybe I should have made that substitution. Let me just move this. Equals 1 times that bracket. But of course, that is now just equal to the right side. So left side is equal to the right side. I have shown that that identity is true. And that's it. Couple of examples. I really wanted to show you the one with the power 4 there because that's one that doesn't occur to students, or it doesn't occur to a lot of students the first time they see it.